Hello guys, today we're going to talk about the MEMIT paper. And before we start, I would love to talk about some prerequisite about the paper. At first, the paper is focusing on a D-layer decoder. Okay, we're not doing an encoder decoder, we're not doing encoder, we're focusing on only decoder architecture. This is very different from, not very different, this is a little bit different from the transformer that most people know, which is attention all you need from that paper. We're just only doing the decoder. Basically, there's an encoder, decoder. In that paper, transformer or attention is all you need. We don't use an encoder. We just use the decoder. And what does it mean by D-layered decoder? I need to emphasize this because this paper talks about this a lot. The D-layered decoder simply means the decoder stacked on top of each other. That's it. Okay. So basically, as you can see, this picture where I found on Google, this one is a decoder. It has the multi-mass attention, has a feed-forward layer, and then you have 12 of them stacked together. Okay. Okay, so what is it trying to do? What is MEMIT trying to do though, right? Like it basically is trying to edit the model. And I can just tell you what it's trying to do by giving you a very simple example. For example, you have your large language model, right? You love your language model, and the large language model is trained from Wikipedia. And when you ask the large language model, hey, what sports does Michael Jordan play? Subject here, Michael Jordan is the subject. Sports is the play sport is a relationship, and it will spit out basketball, right? Which is the object over here, right? Because in Wikipedia, I believe Michael Jordan plays basketball. But let's say somehow, for some reason, you don't want it to be basketball anymore. You want it to be such that next time you ask your model, what sports does Michael Jordan play? It is tennis. Okay. So MEMIT is trying to do is that it is trying to do that. Okay. It's trying to edit the model to a point that it would be Michael Jordan would now play tennis. And it can apply to many other scenarios. You can have you know, Obama, loves eating, blah, 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 blah. So like it can be applied on many other things. And amendment is trying to do that. Um, so first, what we're gonna do is that we're gonna talk about a little bit more prerequisite. The first thing is, oh, and also what makes amendment interesting is that it can edit it in batch. So you can edit a lot of knowledge at one time. So that's also something MEMIT that is very unique to MEMIT. And there's several more prerequisites that I would love to talk about. In MEMIT, it talks about okay, the crucial layers that it is gonna edit. The crucial layers are often denoted as sets out, and it's always gonna be like they're always gonna focus on the last subject token. Now, regarding these two, I would love you to read the paper Rome, where it goes much in depth in that. In Mem, it just, goes through it very quickly, like in just one line. But regarding that, encourage you guys to read Rome. But right now, you can just remember that, okay, they have a set of layers that they would love to edit, which is sets out, sets out, and they will focus on the last subject, oops, the last subject token. And give you an example here, GPJ, the set of layers that they would like to, edit is layer 3, layer 4, all the way to layer 8. Okay. So also MLP, what does MLP refers to? MLP basically refers to the forward layer over here. Let me show you here. Forward layer. The feed forward layer is basically the MLP. And they often have K and M in the paper. What does it mean? Like in the MLP, we have the W in and W out. You have the K is after the W in, and then the K goes to the W out, and then it spits out the M. Okay, so this is the key, and this is the memory. Um, all right, let's look at the equation. So first, this is just a very standard way of representing the D-layer decoder architecture. So you have the hidden layer at L for the token T is basically equal to this right over here. And if you do a little bit of math, you will have this one over here. Okay. And I can give you a quick explanation of why that's true. So you have this one is a layer L. Okay. Like I said, right, the decoder is stacked on each other. You have a layer L minus one. over here. And then HTL goes over here. Okay. L minus one goes over here at token T, and then this is just how the decoder works, they add together, they have the layer norm, blah 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 blah. And then at the end, this one would be MTL plus this one and this one. Okay, so now this equation is quite important, right? Why is it important? Because it shows you that um um each individual MLP contributes by adding to the memory at HIL, okay, as you can see over here, okay, which is later read by the last subject token attention modules. Therefore, when we write new memories into G, what is G? G refers to the model. We can actually spread the desired changes across all the critical layers for L in sets out. Okay, so we're gonna do that later, and just keep that in mind. So what does it mean by the last subject token, right? I always say last subject token. So with recall, right, in the transformer, um the input is always batch times sequence times embedding factor, right? Let's say we have sequence we have only one sequence in the batch. That sequence is of length 3. Okay, then it will look like this. This would be the input. Okay, so you have the batch, the outer array. They have only one sequence, and it's in length 3, 1, 2, 3 over here. And let's say we say the last subject token is the second place, then it would be like here. So this is the last subject token. Okay. So as you can see over here, the input is B cross S cross D, D as the embedding factor, size of the embedding factor. This is the W in, this is the W out, and then the K over here will be batch times sequence times H, whatever this one set it to be. And then when I spit it out, it will be B times S times D. And yeah, so how did they actually do it, right? How did they actually do it? First, we're going to talk about doing it in one layer. Okay, and just a heads up, the W from now on will refers to W out, which is over here. Now for single layer, what we want is that, let's say for single layer at layer L, right? What we want is that um we want to find the W such that it can preserve the old memory and the new memory. Okay. Basically, it's making the distance, the norm here very small. Basically, trying to say that it wants this one to be as close as this one, right? That's what it means by making the norm very small, right? It wants this one to be as close as this one. So what you can see in this optimization equation is that it is basically trying to preserve the old memory and the new memory. Now, to solve this, the paper using normal equations. Basically, what they do is that they start from here, they multiply both sides with this one, and then, the math is done here. You can see it over here. It's very detailed. But I would like to highlight something is that the K0, K02, they do not have access to it because it is in the pre-training process, right? So we need to estimate the K0, K02. And we let C0 to be this one. You will often see C pops up. When you see C pops up, it's basically KKT. Okay, C0 is K0, K0T. Z0 would be the lambda times expected value of KKT factors. Where did they get that from? They get it from Wikipedia. Okay, because they need to estimate it. If you have a better place, you can estimate from there. But they do it from Wikipedia and they find it to be good. Now note that now this is a very important thing. This is just a little bit of linear algebra. Okay, is that K here is a factor, right? But in the code, you will not usually see it as a factor. Now, first you need to know this, right? K1, 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 K1T, K2, K2T, K2, K2T. If you add all of these, this is actually the same if you put all the K's into this one and then one over here, and then you multiply them. So if this is K, this is KT. So this will be equal to KKT. Notice now the K is not a factor. This is a matrix. But the way we do this is the same as this. Okay, so this is just a little bit of linear algebra. And more interestingly, you can actually split it. Okay, if you let's say you can split into batches. So here K1 all the way to Ki, and then Ki plus 1 all the way to N. If you do the math, this one is the same thing as this one, which is the same thing as this one. Okay, just be aware of that. Now, another thing we need to talk about is delta over here. The delta here is very important, right? Delta is equal to RKT. You can just do some math. You will get the same thing. And R here is equal to M, which we refer to as a residual. So it will be M1, which is a new knowledge, minus K1 multiplied on the old model weight. Okay. All right. So what we're gonna look at here is that how we're gonna update multiple layers. Now we know how to update the single layer. Okay. How do we do it on multiple layers? Now recall we have a set of layers we want to edit with, let's say, sets out. Like I said, GPDJ have what? GPDJ has GPDJ, the set out will be this one. Okay. Hopefully that clears up the confusion if you have. Let let L be the maximum layer at R. Okay. And you will also see L, small l, in the paper a lot. It basically means, L is within R. Okay. This one, this is a set of things this is a tuple of things that you want to, this is a tuple, and this tuple represents the things you want to edit. Like I said in the beginning of the video, this one is Michael Jordan, plays sports, and then maybe you want it to be tennis now. Now, basically, what we're trying to do is we want to find ZI, okay, to replace HIL such that adding this thing to HIL would convey the new memory. Now, adding this thing to HIL basically means HIL equal to ZI. Now, this is just a very simple math. So HIL plus delta, right? Okay, HIL plus delta I is basically equal to ZI minus HIL plus HIL, which is basically ZI. Okay, so basically it's just replacing ZI to HI, have ZI to replace HIL. And for each layer in R, we're gonna modify them. That's why we're, updating multiple layers, right? Okay, so how do they do it? First, we need to know how ZI is, done, right? So ZI is done by ZI is done by this equation. How do we find this? We don't really solve this one in a closed form. We use gradient descent. Okay, that's what it says in the paper. Now I'm gonna explain some variables which the paper didn't really go through them. P over here is not probability. It's a scalar. It is the number of prefixes that they have. Okay, this P over here, that is the probability. Okay, G is the model. OI is a desired target. Okay, maybe, like play tennis, right? Tennis. SI, this thing over here is not probability. This thing is a prompt. Okay. For example, Michael Jordan plays sports, something like this. And XJ is the prefix. Okay, they have a lot of different, random prefixes. For example, one of the prefix may be this guy goes to high school. And then that is a prefix. And then you have the prompt, Michael Jordan um plays sports, that is, and OI will be the tennis. Okay. And negative log loss, which is very standard. And yeah. So now we know how to find ZI. How do we spread delta to the layers in L? How do we do that? So for each layer L, we want to find delta L such that if you add delta L to the W out L, then it will it will make this very small. It will minimize this thing. Now, why do we want to minimize this? Recall, if we are minimizing the norm, right? Which means we want this two to be as close to each other as possible. And recall, ZI is something that if you replace HIL with ZI, it will convey the new memory. That's why they're doing this. Okay. And then, they're just telling you again, okay, how does HIL is computed. And then we do it in ascending order. This is very important, from the smallest layer in R to the biggest layer in R. And to find delta L, recall that we have this equation over here. This equation is from here, right? And L is M1 minus W0 K1, right? So you have L to be Mi, and this is the old one, the old weight, right? To be the new, these are the new keys. And I set this to be the Zi minus HIL, and they spread it to, proportion, in proportion. So this is how R is constructed. K is constructed, K over here. Now for each of these factors, how do they find each of these factors, right? They find it using this way. Okay, so they say KRLP over here, once again, is not the probability, it's a scalar. This is the number of prefixes they have. And they add the prefix to the subject. And the K is basically this one here. And this one here is basically referring to this picture over here. Nope, 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 here. Okay. So there's that, and then that's it. Okay. And then we have the algorithm for how to edit the model. This is basically the same as what I've covered above. And I strongly encourage you to read through this algorithm, as that is how they do it. And then let's look at the result. Okay, so they have two data sets. They have the ZSRE, they have the counterfeit. If they look at the ZSRE, first I should talk about what these metrics are. So efficacy is a proportion of cases where, O is the odd max of this one. Basically, it means, how well you edit the model. Paraphrase is how well you edit the model, but, it is paraphrased. So these two are very important to see how successful you are. Um, this one here is your accuracy on random sample unrelated things. And these are the things that it should not change. Now, sometimes a model fail, okay, where it does edit, the new knowledge, but things that are unrelated also change. Okay, so for example, Michael Jordan plays tennis, but somehow Obama is an actor, which I'm not sure. Maybe he is an actor before. So yeah. But you get the idea. And then you have the score, which is the harmonic means of these three metrics. Okay, you can see here MEMIT, perform really, really well. In fact, it performs the best out of all the, fine-tuning, man, and room. Now let's look at the counterfeit. Okay, the counterfeit, also have these things. They're pretty similar to the ones above. But they also have the reference score, right? What does the reference score do? It measures the consistency of G, a free-form generation. Okay, to compute it, okay, what they do is that they first generate the prompt G with the subject S, and then they compute the TF, IDF factors and reference Wikipedia text about O. Okay, so ours is defined as a cosine similarity. Okay, intuitively, GS will match better with O's reference text if it has more consistency, phrasing, and vocabulary. They also have GE, which is a general entropy. Okay, so to check for excessive repetition, which is a common failure. And these are all in the appendix of the paper, which is very helpful. I strongly recommend you guys to look at the appendix, which is at the back of the paper, basically. Now, here are some of the results, okay, in the counterfeit. As you can see, the MEMIT is performing very, very well. Okay, MEMIT is a green line. It's always above a lot of other models besides this one, which, okay, fine, the Meng caught up later on, but it has been winning the entire time. So MEMIT is pretty good in the counterfactual data set compared to other editing methods too. And also we're gonna talk about the editing different categories. Okay, so what they do is that they pick 27 categories from counterfact that have at least 300 cases each and assess each algorithm performance. And it shows that MEMIT is, once again, having a better overall scores compared to other methods. And also, model editing as shown here are often are known to occasionally suffer from a trade-off between attaining high generalization and good specific specificity. I'm not sure how to pronounce that. And it's very visible in men, but for MEMIT, it is achieving a very high score in both of them. Okay. Besides, maybe some special cases. And some of you may ask, oh, does the performance matters on how diverse your categories are? And the answer is no. MEMIT is neither positively nor negatively affected by the diversity of memories being edited. So this is also very good, right? So you don't need to worry about, the memory set is being edited and how it would affect the performance of it. So that's it for the entire paper. I hope you guys enjoy it. Thank you.